recording. Okay. All right. So we looked at diode rectifier circuits the last class. Does anyone have any questions about that? Yes. Oh, it's probably I carried over from like previous quarters. All quizzes, everything's open book, open notes, and open internet. No dial a friend. Final exam is open book, open notes, but the internet usage is restricted to just class material. You can look stuff up. Yeah. But again, that's basically if students understand everything, but it's like an equation sheet where you don't have to worry about trying to make something. Yeah. Yeah. Okay. All right. Where am I? OneNote. Let's see. There we go. It's the more features you add in, the more you have to maintain. And somewhere here there it gets lost. Okay. All right. So 306. And p-n junction electrostatics. That's not for 321 though. All right. Where are we? We are in chapter 1. No, it's still, it's 306. It's 321. All right, there we go. We are on the right page now. All right, full wave rectifier, half wave rectifier. And we saw how the output of full wave rectifier circuits are still not a flat line similar to what we would expect for a DC. So what we need to do is we need to filter out or flatten out the half peaks that we see in our output. And we do that by adding a capacitor at the end of our rectifier circuits, meaning before it gets to the load. And what a capacitor does is, well, capacitor is an energy storage device. If you go back to 201, chapter 3, capacitors and inductors are energy storage devices. They are passive devices, meaning they do not have any energy of their own, but they can receive energy from the circuit and later return it back into the circuit at a later point in time. And so we plug a capacitor into the output of our bridge rectifier circuit. Let's say this is the output of our rectifier circuit. V out, and we connect a capacitor in parallel. It's parallel. It doesn't matter if it's on the left or on the right. Exactly the same thing. But this is V in. And the V in is basically the output of the rectifier circuit. Output of the rectifier circuit. So what happens? Quick illustration. Capacitor receives the energy from the rectifier circuit and then discharges it back into the circuit. So this is the diode output. This actually shows a waveform for a half wave rectifier. Right? Right here, it's off. Right here, it's on. So when the diode is on, you have the half peak, right? And when the voltage is climbing in the diode, the capacitor charges. Capacitor receives energy from the circuit, meaning the rectifier circuit, and stores that energy. Now, when the diode turns off, when it starts discharging, what happens? The capacitor has energy that is stored inside it. It releases it back into the circuit. And so here at this point, capacitor is charging. And then from this point on, capacitor is discharging, releasing back into the circuit. So it's a mix of both chapters 3 and 4 from EE201. Transient analysis, where you receive the energy and then you release it back into the circuit. And of course, the charging time and the discharging time depends on the size of the capacitor, on the circuit components, meaning the resistors. Those are the two primary factors in how fast or slow a capacitor would charge or discharge. Analogy can be made with a bucket of water. The size of the bucket, the larger the bucket, the more water it can store. So the bigger the capacitor, the more energy it can store. The size of the conductor, the size of the pipe, and the flow rate also determine how fast or slow the bucket will fill up. So in a capacitor charging and discharging, size of the capacitor matters, as well as the voltage level or the current that's coming from the rectifier circuit. So we would assume that the size of the capacitor is big enough that will discharge slowly, but it's not that big that will take a very long time to reach full charge. Okay, so in simple terms, here this is showing you that the capacitor is fully charged. So at some point in the past, when the switch was flipped on, capacitor took some time to get going, but once it reaches full charge, all it does is it goes into a charging and discharging cycles. And if the discharging is slow enough, it will not discharge all the way to zero. So this is when capacitor voltage reaches 0 volts. But before it can discharge to zero, the next positive half cycle hits and it begins charging again. Make sense? Right? So the first positive peak, capacitor starts charging. When the diode turns off, no more energy is coming from the circuit, capacitor begins to discharge. If our capacitor is large enough, then it will discharge very slowly. And before it can discharge to zero, the next charging cycle, diode turns on again. Next charging cycle appears, capacitor begins storing, receiving energy again. And so now instead of two half peaks, you now have flattened out the output. So it's somewhere over here. And your output is now right? Yes. On this one? Yes. Yes. Yep. That's the voltage that's coming from the rectifier circuit. So this is sometime in the past. Question being asked was, are we assuming the capacitor is fully charged? The answer is yes, because everything happens instant. Well, I want to say instantaneous, but not quite instantaneously, but happens very, very quick. We flip on the switch, we cannot slow down time. It's 60 cycles in a second, right? So it's 1/60th of a second. So within like less than half a second, just a few microseconds, capacitor is fully charged. Unless we stick like a really huge capacitor in there, then it would take like a few seconds to charge up. But for all intents and purposes, capacitor is fully charged as soon as we flip the switch on. Capacitor receives all that energy and then discharges, charges, discharges. That's all it is. And so what is left behind is basically a ripple. looks like the surface of the ocean. Ripples of waves. Okay. And so this is known as an electrical ripple. And compared to the size of the actual waveform, this ripple is typically in millivolts. Very, very small. Okay. So this was the original diode voltage right here. And this is the output voltage. Right there. Quite a big difference. The circuit provides this energy right there on the left. And when the diode is off and when it's discharging, all of this is provided by the stored energy in the capacitor. So this is capacitor energy. Okay. So this is one of the big applications of using a capacitor. We filter out our AC ripples using a capacitor. Capacitor is very cheap compared to inductors. They're easy to fabricate and easy to integrate into our circuits. Diode current and the load current are shown in this image right here. You can see the load current, when the value is lower, is almost like a flat line, unlike the diode current. Okay. So a couple of equations for the capacitor for a half wave and a full wave rectifier. If you plug in a capacitor into a half wave rectifier, there is a off cycle for every on cycle of the diode. So we need a larger capacitor. So we can design power supplies based on the acceptable amount of ripple voltage, which is VR. Typically, as I said, VR is in the millivolt range. Okay. IL is the average load current and T is the time period. So all intents and purposes, if you're using 60 Hertz, it would be 1/60. Okay, 1/60. If it's a full wave rectifier, we have two peaks, and so we can use a smaller capacitor because a full wave rectifier is supplying. There's no off cycle. It's supplying in both half cycles, right? All right, I have 10 minutes left. Let's move on to Zener. Okay, so if you have a bridge rectifier and we connect a capacitor at the output before it gets to the load, this would be the load right here. Even if the capacitor is, practically speaking, large enough, you would still have some sort of ripple right there. And this is magnified. So this is still not quite a flat DC line. Okay, depending on an application, if it's a very low, low quality power supply or not a critical application, then we might get away with this kind of ripple. But modern electronic devices, we need a almost flat line, actually a near constant DC voltage level. That's where a voltage regulator comes into the picture. So we would take this output and we would connect it to a regulator circuit. The regulator circuit would take the DC input, the filtered DC output from the previous step, filtered rectifier output. We can also call it the filtered DC output, and goes as input into the regulator, and that output of the regulator is going to be a flat line. And by far the most common regulator that we use is a Zener diode. Zener diodes are basically special purpose diodes that are operated in the reverse bias. Okay. And I spoke about the Zener effect. This takes place in heavily doped PN junction diodes. Okay. What happens is in the reverse bias, diode is supposed to be off. It does not conduct, right? But researchers discovered that if you dope the P and N type materials with high amounts of impurity dopants, meaning a heavily doped PN junction diode, at around 6 volts or less, there is an avalanche of carriers crossing over the junction. So you have, without going too much into the physics, you have a PN junction. So it's P and N. And if there's heavy doping, that means there is a heavy concentration of holes on this side, heavy concentration of electrons on this side, right? And then you have the PN junction right here. So if you reverse bias this kind of diode, what happens? Electrons and holes are attracted on towards the voltage supply. So the depletion region keeps on increasing. But at the same time, you have minority carriers that are present in the device. And the minority carriers, meaning there are lots of holes on the N side and lots of electrons on the P side. And they are pushed to the junction. And so these minority carriers will cross over the junction, will result in a heavy flow of current, or a heavy flow of charge carriers, which results in a heavy flow of electric current that is independent of the applied voltage. And you can see that right here. Because of the heavy influx of charge carriers crossing the junction in reverse bias, a current is established. That current is independent of the voltage, meaning until a certain voltage level is reached, your current is almost equal to zero. After that voltage threshold is crossed, or threshold voltage is crossed over, the heavy current starts flowing and the voltage remains near constant. Okay, voltage remains near constant. So reverse bias, there's barely a gap. More often than not, in real life diodes, it's like a flat vertical line. And this is known as the Zener breakdown. There's a second effect that takes place in reverse bias, and that is avalanche effect due to impact ionization. It's because when you're applying a voltage, the electrical energy is transferred to the carriers. The holes and electrons that are moving through will start moving randomly through the circuit. And because of the heavy doping, there's a large number of these charge carriers present. Each one of these will impact or hit other atoms, dislodging more charge carriers. Those will in turn acquire energy and flow through the lattice structure, and in turn collide with other atoms, thus releasing more charge carriers, and so on and so forth, until more and more charge carriers are created. Because it happens due to the collision of charge carriers, this is known as impact ionization. More and more ions are created because of collision, because of impact. And it creates a cascading effect or an avalanche effect. So at one point, the junction will break down, it'll overheat, and it'll just blow up. Okay. So the process is known as impact ionization, and it is known as avalanche breakdown. So it's avalanche breakdown due to impact ionization. Okay, avalanche breakdown due to impact ionization. Zener breakdown only occurs in heavily doped PN junction diodes. This is typically less than 6 volts. Avalanche breakdown is typically higher than 6 volts. Okay, but generally speaking, all breakdown in the reverse bias is now referred to as Zener breakdown. Even though that's technically two separate mechanisms, when you operate it in the reverse bias, we just say it's Zener breakdown, even though technically it may not be. Okay, the demarcation line is around 6 volts. So Zener diodes are exclusively used in the reverse bias. The symbol is shown right here. The cathode has whiskers. Oh. Cathode is still the cathode, anode is still the anode, but a Zener is noted with whiskers. And it's exclusively operated in the reverse bias. Diode voltage is always taken as positive at the anode, negative at the cathode. Because the Zener diode is used in reverse bias, the diode voltage for a Zener diode is always negative. Okay, it's always negative. However, Zener voltage will be treated as positive. So plus Vz will always be minus Vd, because Zener diodes are exclusively operated in the reverse bias. And that is illustrated by this equivalent model right here. In the forward bias, we can treat it as a diode, a regular diode. Regular or normal diode. But its application is based on using it in the reverse bias. So in the reverse bias, we can model it as a diode with the resulting voltage Vz that is required to overcome that breakdown. In forward bias, of course, you have a forward bias diode and the junction potential, which is 0.6 or 0.7 volts for silicon. And then, of course, VZ can be designed to be anywhere between a few volts up to tens of volts. I believe in your lab, you're going to use a Zener that's about 6 or 7 volts. So VZ is part of the spec, and PZ is the maximum power that the Zener can dissipate. The way we use it for a regulator circuit is by connecting it parallel to a load. I think I'm almost out of time. So I'm going to keep on going. If you need to leave class, feel free to do so. And you connect it in parallel to the load resistor. Diode is connected in reverse bias. As you can see, output is positive at the top, negative at the bottom. Diode voltage would be negative. Again, reverse bias. And the way it would work is this would be a series current limiting resistor. We do not want to blow it out, of course. So we have a current limiting resistor in series. Current's going to go and flow in this direction. And the way it would work is, as long as the input voltage to the Zener is below 6 volts for VD, or I would say, let's say our series resistor is 0, input voltage VSS or Vin is less than VZ, the Zener voltage, then diode remains off. And whatever you apply at input, you will expect at output. So V out would be V in. For VSS or V in greater than VZ, the diode turns on. When the diode turns on, it will allow current to flow through. Even though we say that ID and VD are flowing in opposite directions, the Zener voltage and Zener current would be flowing according to the normal sign convention. So V out would equal to VZ. The Zener diode will permit excess current flow in voltage constant. Okay, there are two parallel paths. If you increase V in, if V in goes up, that means that the load voltage should also go up. The current goes up, right? So if voltage from the supply increases, then the total current coming from the power supply increases. If the total current coming from the power supply increases, your IL and IZ should also increase. But if you want to maintain the voltage at the output load, that means the excess current that's coming from the power supply should go somewhere else, and it goes to the Zener diode. Okay. Thus, the output voltage and output current remains constant. The excess current goes to the Zener diode. And we'll expand more on this on Wednesday. And if you have any questions, please feel free to reach out. Okay. So we'll end class here today. Let's see.